Good afternoon, everybody, and welcome to another Geo-Institute live stream. Today, the occasion is part 3 of 3 in the Maccaferri live series. If you did not get a chance to see parts 1 and 2, you can head back and catch those archived on our YouTube channel, and we'll put links in the chat where you can click back and see those. For now, though, my name is Brad Keeler. I'm the Geo-Institute Director, and we're thrilled to have you with us today. If you don't know anything about the Geo-Institute, after you watch this, you'll want to head on over to geo-institute.org, and there you can learn all kinds of things about us, including that we are a technical society with about 12,000 members, most of whom are geotechnical engineers and or geologists, and that we are part of the American Society of Civil Engineers. And if you like what you see today, and you guys stick with us, the viewers come back every time, so you want to click like, subscribe, and get notifications, and we will let you know every time we post something to the YouTube channel. Now, our feature presentation, part 3 of the Maccaferri live series on Rockfall Barriers and Attenuators. Here to introduce our speaker today is Sebastian Derringer. Sebastian, thanks for coming back and doing this for us again. We appreciate it. Take it away.
Thank you. My name is Sebastian Derringer, and I'm a professional engineering geologist. I work at Landslide Technology based out of Portland, Oregon. Today, I have the pleasure of introducing you to Mike Koutsaris, who is a professional engineer and is the Geohazard Mitigations Business Unit Manager of North America for Maccaferri Incorporated. Mike has a Bachelor in Science in Civil Engineering from North Carolina State University and an MS degree in Civil Engineering from Georgia Institute of Technology. Mike is a geotechnical engineer with over 34 years of experience and has authored and presented several technical papers at various industry conferences throughout his career. For the last 6 years, Mike has been an officer of the Association of Geohazard Professionals and chairman of ASTM Subcommittee for Geohazard Netting. So with that, Mike, take it away.
All right. Thanks, Sebastian. Good afternoon. My name is Mike Koutsaris. I'm the Geohazard Mitigations Business Unit Manager of North America for Maccaferri. For those of you that are tuning in for the first time, Maccaferri was established 144 years ago and has been manufacturing and supplying geohazard mitigation systems throughout the world for over 60 years now. We're recognized as a leading innovator and manufacturer of geohazard mitigation systems, and we currently have over 3,000 employees and service over 130 countries worldwide. I want to welcome you to our third Geohazard Mitigation live stream webinar on dynamic rockfall barriers and attenuators. As mentioned, this live stream webinar is the third Geohazard Mitigation webinar in which we'll discuss dynamic rockfall barriers and attenuators. If you missed either of the first 2 webinars on simple and pin drapery systems, as Brad mentioned, you may still view them on YouTube. Also would like to mention that we do offer a 1-hour PDH certificate for this and any of our other webinars. Here's a brief outline of today's webinar. We'll cover the applications of using dynamic rockfall barriers and attenuators. We'll also discuss research testing that's conducted, metrics used to evaluate performance, and how these systems are designed and installed. We'll explain the various Maccaferri systems and showcase some case histories. As explained in previous sessions, rockfall solutions can be categorized into one of 2 methods. The first method is to control or contain the hazard at its origin. And the second method is to protect or intercept the hazard after its detachment. So choosing the right mitigation system requires the designer to consider its placement proximity to the detachment area of the hazard and its most effective placement location. As you can see here, and what was explained in more detail in our first 2 webinars, simple and pin draperies are used to contain and control surface instabilities and are placed close to the detachment area, and they extend from a higher elevation than the detachment zone of the hazard. Whereas rockfall barriers and attenuators, as we'll discuss in this webinar, are used to protect and intercept the rockfall hazard after its detachment, and they are installed at a lower elevation than the detachment zone of the hazard. Dynamic rockfall barriers are considered passive protection systems. They don't prevent the hazard from occurring, they intercept it and protect against it doing damage. It's necessary to determine the energy that the protection system must resist, as well as the protection system's required height and allowable deformation to keep the hazard from impacting adjacent people and infrastructure. Rockfall barriers can resist energies from 10 kilojoules to 10,000 kilojoules. We generally categorize barriers with capacities of less than 100 kilojoules as low energy barriers, and between 100 kilojoules and 5,000 kilojoules, we tend to classify them as medium energy level barriers, and greater than 5,000 kilojoules can be classified as high energy level barriers. A rockfall barrier consists of many different components. The main elements are the posts that are tied into the foundation components and the interception panels, which are hung between the posts. However, there are also cables, anchors, and dissipators that are connected to these posts and interception panels that fully comprise the barrier system. The posts in the far left photo will determine the interception height of the barrier and hold the interception panels in place. The next photo shows the cabling, upper and lower longitudinal cables and upslope bracing cables that connect the interception panels to the posts. The third photo shows the interception panels, which of course block the boulder during its motion. And the fourth photo shows the energy brakes or dissipating devices, which help to dissipate the energy from impact. And finally, the anchors transmit the impact forces to the foundation. Before we can apply a barrier in the field, we must know its limits. So we must first perform research testing to determine the barrier's performance. The European Organization for Technical Approvals, EOTA, developed a guidance approval of falling rock protection kits, and this is referred to as ETAG 027. So rockfall barriers are tested in accordance with ETAG 027, and if passing the performance evaluation, the barrier is awarded a certification or CE marking. So ETAG 027 has been a guideline for European technical approval of falling rock protection kits. Now, this defines the methodology to carry out full-scale field tests, and it defines the materials used for rockfall barriers. After the barrier is tested and evaluated, it receives a CE marking certification. And here's a short video showcasing the ETAG 27 test. So the EAD 340059 document applies to barriers with energy levels greater than or equal to 100 kilojoules. This standard defines two energy levels for each barrier classification: the maximum energy level, or MEL, and the service energy level, or SEL. As you see here, there are several energy level classifications starting from 100 kilojoules and up. And there's a newly developed standard, EAD 340089, which applies to barriers less than 100 kilojoules. That's what we refer to as lightweight barriers. So one main part of the testing evaluation is to determine the barrier's maximum energy level capacity, or MEL. The maximum energy level is defined as the highest level of energy that the barrier can withstand. However, the barrier would actually be guaranteed to resist that energy. So it's in essence a minimum level of resistance for that barrier. It's certified to that specific energy level, but it will withstand impacts at least at that level. The barrier is considered to have passed a particular MEL if it simply stops the block upon direct impact at that energy level. Another important part of the test is to determine the service energy level of the barrier, or the SEL. The service energy level is equivalent to 1/3 of the MEL, and the barrier is required to withstand 2 impacts of that energy level without having to be repaired after the first impact. So in essence, this is thought of as an energy level for which there is no need of maintenance after 1 impact. So if the barrier is being tested at a maximum energy level of, say, 3,000 kilojoules, it would have to sustain 1 impact of 3,000 kilojoules and 2 impacts of 1,000 kilojoules, which is 1/3 of the MEL. And then the SEL test is passed if number 1, the barrier stops the block, and number 2, the residual height after the first impact is at least 70% of the original height of the barrier tested. Barriers are typically tested with a vertical drop of a reinforced concrete block of known dimension and density. And the mean velocity of the block within the last 3 feet from the contact point with the net must be at least 25 meters per second. So the impact energy is equal to the kinetic energy of the block given by the equation energy equals 1/2 times the mass times the impact velocity squared. The tested barrier is installed with 4 posts providing 3 spans, as you see here. The test is conducted with the block impacting the barrier in the center of the center span. Because the test is performed on a barrier with 3 spans, it is always recommended to install barriers in actual field conditions with at least three spans so as to conform to the actual test conditions. Further, the EAD certification is applicable to tested barriers, but within certain geometrical limits of the barrier's height and post spacing. For example, if a barrier was tested with a height of 3 meters, you wouldn't be able to construct this barrier on your project to a height of 6 meters and still be in compliance with the certification. The same applies to post spacing. If the tested barrier was tested with a post spacing of, say, 10 meters, you wouldn't be able to construct the same barrier with a post spacing of 5 meters and still be in compliance with the certification. So these geometrical changes will affect the barrier's performance and the foundation loads. So please keep this in mind. This chart gives you an example of the height and post limitations for each Maccaferri barrier to maintain compliance with the EAD certification. As you see here in this chart, there's an upper and a lower limit for both the barrier height and the span width, or often referred to as post spacing. These upper and lower limits are based on the certification guidelines as applied to the actual tested barrier's height and post spacing. During the field testing, the primary items that are recorded are the barrier deflection, the residual height, the lateral gap dimension, and the foundation loads. We'll further discuss each of these separately. So one of the key performance features recorded during the test is how much the barrier deforms or elongates when it's impacted. Remember, these are not rigid barriers. They will deform or elongate upon impact. In fact, the energy is absorbed by the barrier as it deforms. So energy dissipation through deformation. It is particularly important to know the barrier's deformation upon impact when designing a barrier close to infrastructure. Another key performance indicator is the barrier's residual height. So the barrier height is determined as the distance between the upper and lower longitudinal cables located at the top and bottom of the interception panel. As the barrier is impacted and the interception panel elongates, the height of the barrier is pulled down to its residual height. So this residual height is measured as a percentage of the barrier's original height before impact. So the greater the barrier's residual height, the better the barrier has performed. The lateral gap is another important parameter recorded during the test. As you see here, as the barrier is impacted, the interception panel may pull away from the adjacent post, as you see to the right, the photo to the right. So this, as the interception panel may pull away from the adjacent post, it leaves a certain distance, or it could leave a certain distance of unprotected coverage. So the smaller the lateral gap distance, the better the barrier has performed. The lateral gap should be considered during the design phase in order to ensure that the required protected area and the length of the barrier are equivalent. Otherwise, there may be a need to add extra length to your barrier in order to ensure full coverage of the hazard area. Essentially, all of these recorded performance features, barrier elongation, residual height, lateral gap distance, they determine how well the barrier maintains its initial configuration after impact and is therefore able to maintain its protection as originally intended. In summarizing the Maccaferri portfolio of tested and certified rockfall barriers and their performance, here you'll see that Maccaferri offers a full range of tested and certified barriers ranging from 35 kilojoules, which is our RB35035 barrier, to 9,000 kilojoules to handle your site-specific conditions. So we can also custom design specific barriers for special cases, and any custom design that we do is based on the data that's developed from these tested barriers. Looking at the specific performance features of rockfall barriers, of Maccaferri's barriers, the maximum elongation of Maccaferri barriers are amongst the lowest in the market. The residual height of the Maccaferri barriers are among the highest in the market, in the highest category A. Maccaferri barriers have no lateral gaps after impact, so there's no need to add any additional span of coverage. And after 2 service level energy impacts, Maccaferri barriers still require no maintenance. Remember, the certification only requires that after the first service level energy impact, no maintenance is required. In our case, all of our barriers, even after 2 service level energy impacts, still no maintenance is required. Now moving into the design of rockfall barriers. The first step in the design process would be to understand the external structure of the rocks in relation to the topography of the slope, the geotechnical parameters and cross-section of concern, to understand the source of the rockfall event and its path down the slope. The next step is to model the rockfall and select the barrier design parameters. 2 software programs are often used for this purpose. One is the Colorado Rockfall Simulation Program, referred to as CRISP. The other is a Rock Science Rockfall program, assesses slopes at risk for rockfall. So first we need to model the type of instability. Specifically, is the rock free falling? Is it bouncing, rolling, or sliding? And we need to determine the initial velocity, acceleration, and position of the free fall. So an understanding of the source of the rock fall, the design rock size, the path down the slope, the bounce features, velocity, and kinetic energy are important in order to determine where the barrier would need to be placed, how high the barrier needs to be, and how much energy the barrier needs to resist. The next step is to evaluate the substrate and the rockfall impact rebounds that might occur. And then finally, we need to apply those same steps for all the potential rockfall trajectories and statistically analyze the results for use in the barrier selection. Next, we need to determine where the barrier should be located. Barriers are less efficient if they are built in ditches or at the bottom of a vertical rock slope, as shown in the top two positions in the diagram on the right. For instance, in positions A and B in the diagram, you see that the rock could jump over the barrier. Position C is a good position, even if its assembly is more work than position D. In position C, the blocks have low speed. They proceed slowly with little rebounds. And then in position D would even be better. Once again, it's in a position where the blocks would dissipate, the energy would have been even further dissipated. The rebounds would be reduced, but it's also easier installation because it's located close to the street. The rockfall simulations will allow the designer to determine the energy that the rock will produce and the barrier must resist. So it's important to know, once again, both the maximum energy level, or the MEL, that the rock will produce, as well as the energy of the more frequent rockfall occurrence, which would represent the service energy level, or the SEL. The design barrier energy level should be the greater of either the maximum energy level or 3 times the energy level of the more frequent occurrence, or service energy level. So it might also be prudent to apply a safety factor to your design energy level, depending upon the risk to human life and whether the protected infrastructure is stationary. For instance, if the protected infrastructure is stationary, then there is a higher probability of damage should an event occur. This would warrant a higher safety factor for your design energy level and barrier height. When a rockfall barrier is placed, we have to verify the minimum distance between the barrier and the road or building to be protected. So barriers are designed to deform in a controlled manner in order to dissipate the rockfall energy. So we must make sure that the barrier elongation or deformation upon impact is within an acceptable distance. And the placement location of the barrier must consider how much the barrier is expected to deform upon impact. As mentioned before, Maccaferri rockfall barriers have among the lowest deformation after MEL impact available in the market. The minimum height of the barrier must consider the size of the rock and its expected bounce height. Remember, the field testing that is conducted on rockfall barriers ensures that the rock impacts the interception structure in the middle of its height. So in designing the barrier height, we want to keep that in mind and strive toward keeping the rock impact within the central portion of the barrier. So the residual height of the barrier, as mentioned before, is the barrier's height after impact as a percentage of its initial height. So the greater the residual height of the barrier, the more likely it could stop a multiple impact event. Therefore, you would want a barrier that achieves a residual height of at least 70%. Maccaferri Rockfall barriers have among the highest residual height after MEL impact available in the market. The lateral gap performance of the barrier is another important aspect to consider during the design phase. The lateral gap distance measured during the full-scale field testing of the barrier will determine whether the length of the barrier would need to be extended in the field in order to fully protect your desired infrastructure. Note that there are barriers on the market with lateral gaps of nearly 4 meters. This would require an additional 8 meters of barrier length to account for the lateral gaps on each end of the barrier. And once again, Maccaferri barriers do not have any lateral gaps after MEL testing. Now we'll finish up the design discussion with these next few slides on various considerations that can influence barrier performance. Let's first recall the full-scale field testing that is performed on these barriers. In the field test, the impact is a direct translational force. Rotational forces are very low or non-existent. And the impact is in the middle of the interception panel within the center of 3 spans. So simply speaking, any time the impact is different than that of the controlled field test, theoretically the performance of the barrier can be compromised. Now that doesn't mean that the barrier will fail, but it does mean that damage might occur and the performance of the barrier won't necessarily be exactly as anticipated. After all, we can't always predict where the impact might occur. So as you see in this slide, the barrier might be hit at the very top of the interception panel or close to or directly into the post. This, of course, would likely damage the post and base plate that would then need to be replaced. However, overall, you could expect that the barrier would at least stop the rock from passing through. In this case shown here, the barrier was designed for a single 3,000 kilojoule impact, whereas it was impacted multiple times, almost like a debris flow, with the largest impact being greater than 4,000 kilojoules. Even in this case, the barrier performed well and prevented rock from penetrating beyond the barrier. So once again, I'll point out that a barrier that has been tested to a certain maximum energy level really means that it will perform to at least that energy level. It's also important to consider the elevation difference between the posts. For instance, a high elevation difference between the posts may result in stress variations on the barrier elements, which are difficult to quantify. So it's best to install the barrier with minimal post-to-post elevation difference. The maximum elevation difference between posts is anywhere from 1% of the post spacing to 10%, depending upon the stiffness or flexibility of the interception panel. We would suggest you check with us on our recommendations for a particular barrier system. Referring once again to the ETAG testing, if you recall, the barrier would have been tested with 3 spans, and each span was about 10 meters. In other words, there were 4 posts, and each post was spaced 10 meters apart. So the total length of the barrier tested was 30 meters. So in order to conform to the barrier certification, we need to remember that we need at least a 3-span barrier, and the post-to-post spacing must be within a certain distance of the tested barrier's post spacing. For instance, if the post spacing of the tested barrier was 10 meters, then the post-to-post spacing can range from, say, 8 to 12 meters in order for the certification to remain applicable. As you see in this slide, for instance, a 10-meter long barrier would not be in accordance with the barrier certification. You simply couldn't build 3 spans with an acceptable post spacing that would adhere to the certification restrictions. A 30-meter long barrier, however, could be built with 3 spans, each with a 10-meter post spacing. In fact, that's exactly what is used in the field test. For longer barriers, say you've got a 180 meter long barrier, you could build it as one single barrier. However, you might also consider breaking that into smaller barriers. So there's different options here on post spacings as well. So for instance, with an 180 meter long barrier, you could go with a single barrier with post spacings of 12 meters, for instance, or you could have 18 spans at 10 meters. You could have, you could have a 12 meter post spacing and you'd have 15 spans. So there's some different combinations that can be done there. Or you could break up that single barrier into 3 separate barriers. As you know, they're overlapped a certain distance. But in this case, for instance, it might make sense to have 3 60 meter long barriers or so. And that leads to this final consideration relating to how much overlap is required for a multi-segment barrier. So going back here, you see that if you go to 3 segments, multi-segment barrier, you've got some overlap here. And so we have to determine, well, how much overlap do we need? That's going to be a function of just how far apart vertically these barriers are. The whole point is to keep the rock from passing by one barrier and then squeezing through the second barrier. So the lateral overlap distance is dependent upon how far apart the barriers are placed. The further apart the barrier segments are located, the more overlap is required. So of course the purpose of the overlap is to keep the boulders from penetrating between the adjacent segments of barrier. When developing a specification for a rockfall barrier, these are the items that are most important and necessary for us to offer a price quotation on the system. We need the energy rating, the energy level that we're looking at. And once again, you can either determine that based on the maximum energy level that you're expecting. But let's say the maximum energy level that you're expecting is 3,000 kilojoules, for instance. But you've also determined that the service energy level, the more frequent occurrence, might be on the order of 1,500 kilojoules. In that case, you would take the 1,500 kilojoules, the service energy level, and multiply that by 3, and that becomes 4,500 kilojoules. So in that case, you have a maximum energy level of 3,000 kilojoules, but the SEL times 3 is 4,500 kilojoules. Therefore, you would need a barrier of at least 4,500 kilojoules, and you would specify a 5,000 kilojoule barrier, because that would be the classification according to ETAC. So a 5,000 kilojoule barrier in that case would be what would be needed. We also need to know how high you want the barrier. Okay, so the barrier height and how long, of course. What is the area of coverage we need? Is there a minimum and maximum post spacing? Once again, there's a range there. We can't just pick and choose whatever post spacing we want. We have to maintain our certification. If you wanted to leave that to us, we could do that as well, and we would offer post spacings that maintain our certification. We need to know the foundation information. Are we dealing with soil or rock? And then whether or not there's a secondary netting that is required to catch the smaller rocks. So we test our barriers without a secondary netting so that it's not necessary with our barriers. But a secondary netting could be used. Once again, it's installed simply to prevent the smaller rock from washing through. And then, of course, are there any Buy America or Buy American requirements that are required for us to pay attention to? The next few slides will quickly walk through the installation process. So prior to construction, the contractor will inspect the site and lay out the barrier alignments and the post locations. Then they'll verify the tolerance for alignment and orientation and elevation. Depending upon the ground morphology, it can be convenient to prearrange a concrete pad underneath the base plate so that it leans with the substratum of the underlying rock. In setting up the posts, the contractor will locate and install foundation bar anchors according to the geometry of the post base plate in accordance with Maccaferri standard foundations. Axial pull-out capacity should be verified as per the specifications. Then the contractor will place the base plate, ensuring the correct orientation. Then the contractor will fasten and secure the base plate to the anchors in accordance with the Maccaferri installation guide. The next step would be to install the wire rope anchors. The contractor will inspect and locate the upslope cable anchors, noting the ground conditions and the correct offset to the barrier alignment. Drill hole diameters according to Maccaferri's standard foundation literature, and place centralizers to position the anchor in the center of the drill hole. And then once the anchors are installed and the grout has cured enough to achieve specified compressive strengths, you'll want to test all lateral anchors and 50% of the other anchors. Next, when installing the posts will be placed on the ground straight upslope and aligned with the base plates. With the posts on the ground, the contractor will place the lateral and upslope bracing cables through the post fair leads. Once again, the contractor will refer to the Maccaferri installation manual for the details. Then when installing flexible post barriers, the contractor will insert the center bolt in the prearranged base plate slots at the base of the post and then secure it with a nut. In this way, the hinged joint of the post is realized. Next, the contractor will install the longitudinal cables and raise the posts. The posts will be elevated to their upright position. The downslope turnbuckle device is set up, securing it to the base of the post. The turnbuckle device is adjusted to achieve the correct inclination of the post. At this point, the post is self-standing and final connections to ground cable anchors are made, and the upper and lower longitudinal cables are placed in position and connected to respective anchors. Finally, the interception panels are then connected to the upper and lower longitudinal cables. And the interception panels are connected to lateral end posts through the lateral junction cables. And then if not pre-attached, the secondary layer is then attached to the main interception panel. As a rule, the various elements of the Rockfall barrier require repair or replacement only as a result of impacts. A barrier should be checked immediately after each rock impact and periodically to ensure the satisfactory condition of the barrier and its components. It is necessary to check the interception panels, which must be kept free of obstacles of significant size that may affect the dynamic range of the system in the case of a significant impact. Maccaferri does offer checklists and maintenance manuals for easy reference. Accumulated debris from landslides or rockfalls should be removed from the barrier prior to full assessment of the structural condition of the barrier, as it is often the case that compromised components will have been obscured by fallen material. So accumulation of soil and rocks behind or on the barrier may have effects on the system performance, and deposits that are allowed to change the local slope morphology may affect the trajectory of falling rocks. Maccaferri's rockfall barriers were designed with an emphasis on the durability of the system, meanwhile requiring minimal maintenance, with obvious practical and economic advantages. Now I'd like to introduce you to Hellomac. Hellomac is a safety feature available from Maccaferri rockfall barriers. It's an alert system installed on the rockfall barrier, and it detects when a rockfall event has occurred. It alerts the public and authorities of the event by sending a notification via text message, email, or mobile app. Hellomac has been calibrated and tested by the Polytechnic of Milan. Hellomac is designed to be used as an event alert system. Hellomac can be deployed on new rockfall protection systems, or it can also be retrofit to existing systems, including those of our competitors. Hellomac can also be used to investigate and monitor the need for future rockfall protection system at specific locations where natural events might occur, thus enabling decision makers to decide if and where to install a rockfall protection system. For example, it can be installed on a site with a high risk of an event to record all the history of the events to help determine whether a protection system is necessary in the future. In this case, it could also be used to connect Hellomac to sirens or signals to alert people in case of an event, even when no protection system has yet been installed. Here we see what Hellomac looks like in reality, where it is installed, for example, at the top of the post on a rockfall barrier. As you can see, it's very small and it doesn't affect the barrier in any way. The device can be installed either upslope or downslope on the barrier, but we recommend installation downslope to prevent its impact. It is not mandatory to install the Hellomac to the barrier post, but for rockfall barriers, the rear of the post is considered a safe position for the device. The connection of the Hellomac to the barrier is very simple. The end of each arm is fixed to the specified area of the barrier. The rest of the wire, wound in a ring, is extended along the net and supported in specific points along the netting. The length of the wire is specific to the barrier being monitored. The arms connect the disc to the different positions on the rockfall protection system. So a single device is enough to monitor the impact in 8 different locations within 2 adjacent panels, 4 on each panel. We'll now finish the rockfall barrier section of the webinar with some case histories. We'll start our case histories off with our lightweight barriers. This is a Colorado DOT project along I-70 in Glenwood Canyon. It's a 1 mile long, 35 kilojoule barrier installed on top of a Jersey barrier with posts spaced every 30 feet, installed by Rock Solid Solutions. This barrier is tested in accordance with European testing and certification standards and provides low elongation upon impact, making it suitable for roadway applications for barrier heights of 6 to 8.5 feet. The interception panel is a 3.4 millimeter double twist wire mesh manufactured with a border cable. This case study features the same solution implemented on an access road to Marine Base Camp Pendleton in California. It's a 700-foot long by 6 foot high, 35 kilojoule K-rail mounted barrier with posts spaced every 20 foot. As depicted in the photos, it is clear to see why this is an easy installation barrier. The barrier posts are anchored into the back of the K-rail, enhancing the load transfer into the concrete barrier. Additionally, the lateral anchors are directly secured into the K-rail, and it's worth noting that standard chain link fences mounted on K-rail are often used to provide a solution for similar applications as a lightweight rockfall barrier solution in roadside applications. However, these systems are not always tested or rated. As mentioned before, the Maccaferri lightweight barriers are tested and certified to guarantee the functionality of the barrier in these critical roadside applications. This project is situated along I-90 in Idaho between Wallace and Mullen. The Idaho DOT specifications called for a 650-foot long K-rail mounted rockfall fence. Maccaferri again provided its tested 35 kilojoule rockfall barrier. Along with providing for easy and fast installation, this lightweight roadside barrier features multiple standard foundation configurations, such as being mounted on concrete barriers directly embedded in the ground or self-standing. The solution highlights the adaptability of standard foundations for rockfall barriers, and is another great example of an application where a rockfall barrier is necessary and the assurance of having a tested and certified system is essential. This project is situated along US Route 129 near Knoxville, Tennessee. Tennessee Department of Transportation project. As part of the current roadway project, the contractor was tasked with providing a temporary rockfall barrier for both workers and the public throughout the duration of the project. Typically, a standard temporary movable rockfall barrier is installed and anchored on top of trench plates and moved from location to location. However, this can be costly and difficult and inefficient for the contractor. So the solution proposed by Maccaferri offered a more efficient alternative using a fixed braced post that eliminated the need of upslope anchors. Despite the need to cover a vast area of 4,200 linear feet for the project, the contractor opted for this solution over a movable barrier because of its ease of installation and maintenance. This is a Puerto Rico Highways and Transportation Authority project along PR 333. A Maccaferri 500 kilojoule cantilever barrier was installed, which uses the patented high energy absorption primary catchment netting. The HEA panels provide very high energy absorption capacity at low deformation as compared to ring nets and other nettings in the market, saving an additional 7 foot of space adjacent to the highway. The barrier was installed along 328 feet of highway at a height of 10 feet and was manufactured with stainless steel to protect against the harsh tropical environment. This project is a Maryland State Highway project located in western Maryland on Interstate I-68, referred to as the Sidling Hill Slope Protection. Construction of the barrier was completed in 2023 with a total of 1,480 linear feet of rockfall fence successfully installed. Schnabel Engineering designed the rockfall barrier to withstand an energy capacity of 800 kilojoules with a maximum deformation of 11 feet from the face of the posts. To meet these requirements, Maccaferri proposed a semi-rigid rockfall barrier using its patented high energy absorption cable nets, featuring 1/2-inch diameter cables arranged in a 10-inch by 10-inch pattern. Unlike traditional ring net barriers, this heavy cable net offers a stiff response to deformation, effectively reducing the barrier deflection. Here we have some close-up photos of the low deformation Maccaferri HEA cable net. We can also see the smaller opening double twist wire mesh attached to the cable nets in order to capture small rock debris. As evident from these photos, the implementation of the low deformation Maccaferri high energy absorption cable net enabled the barrier to be strategically positioned approximately 11 feet away from the shoulder, optimizing its effectiveness. However, it also results in increased loads. As we stiffen up the barrier, we increase the loads on other components of the system. So to counter this, Schnabel Engineering designed heavy cantilevered posts capable to withstand this increased load. Here we have another promotional video. This project along PennDOT Route 15, just north of Harrisburg, Pennsylvania, has steep slopes ranging up to 78 degrees and 240 feet in height, resulting in very large rockfall impact loads of 2,000 kilojoules, which had to be resisted without deflecting beyond the roadway edge. The primary challenge for this project was the very limited lateral space between the high rock slope and the highway. The site required the construction of roughly 1,400 lineal feet of rockfall barriers along the tight shoulder. The maximum allowable barrier deflection upon impact was selected to avoid possible encroachment in the travel lane. Impact and deformation analyses determined that standard flexible rockfall barriers available on the market could not be used because the elongation would have far exceeded the allowable value for the specified impact energies. So Maccaferri custom designed a semi-rigid barrier with its high energy absorption panels to meet the deflection limits dictated by the location of the roadway. This custom designed Maccaferri semi-rigid HEA barrier was found to have approximately 20% better deflection performance than other types of barriers on the market, and which satisfied the deformation limit requirements for this project. The proposed improvements of this project were to manage a rockfall area along a portion of the Keane Road in Maui. The proposed rockfall mitigation improvements extend along approximately 900 feet of cliff face along Keane Road and include this 1,000 kilojoule cantilever rockfall barrier along the rock cliff. As you see here, the barrier was impacted shortly after installation and performed as designed. Wyoming DOT here was faced with a large outcrop of potentially unstable rock beside the very heavily traveled east entrance to Yellowstone National Park. The design showed that the dynamic rockfall protection barrier needed to be 20 foot high and protect over 450 linear feet of highway. The Maccaferri 2,000 kilojoule barrier was chosen and successfully installed by Rock Solid Solutions after the summer tourist season. And due to space limitations, the barrier was installed exactly 20 feet away from the shoulder line of the highway, where the tested elongation of the Maccaferri 2,000 kilojoule barrier was 19.7 feet during a maximum energy level event. This is a Colorado DOT project along I-70 westbound, just west of Hanging Lake Tunnel. CDOT originally installed a 16-foot high 2,000 kilojoule barrier that had seen several impacts and later upgraded to a 20-foot high 3,000 kilojoule barrier for a 150-foot long span. This is a Tennessee DOT project requiring a 3,000 kilojoule barrier. As you can see here, there is only a very minimal shoulder and almost no catchment area for falling rock. So this lack of catchment, along with the steep slopes and blocky nature of the bedrock, created a high priority rockfall hazard for Tennessee DOT. Last year in early February, several large rocks came down on the Kamehameha Highway on Oahu's North Shore. This beach, the Waimea Beach and Waimea Valley Waterfall, is a major tourist attraction, and the highway hosts thousands of cars per hour. The Hawaii Department of Transportation fast-tracked the construction of a 16-foot high, low elongation rockfall barrier and contracted high-tech rockfall for installation of the barrier. The Maccaferri 3,000 kilojoule ring net rockfall barrier with a secondary cable net to limit elongation was chosen because there's such little shoulder to accommodate conventional rockfall barriers. This is an Ohio DOT project along US Route 52 in Union Township, Ohio. US 52 is a major highway that runs east-west along the Ohio River across southern Ohio. Several instances of very large rockfall have occurred on this highway where a house-sized boulder fell near Ironton in 2015, and again near Chesapeake, where a rock slide brought multiple large boulders onto US Route 52, closing all 4 lanes of traffic in February 2018. To mitigate the rockfall hazard, the Ohio Department of Transportation performed a rockfall mitigation project that included the installation of a 5,000 kilojoule rockfall barrier supplied by Maccaferri. The installed barrier spanned 275 feet in length and was 15 foot high. The last series of slides will describe hybrid barriers and attenuators. As you see in this slide, hybrid barriers and attenuators can be described as having a rockfall drapery that is hung freely from the top of a barrier post and extending down the slope a specific distance. For a hybrid barrier, the tail end of the drapery section is anchored in order to secure the rock and not allow it to exit the system. An attenuator, on the other hand, is a catch and release system that dampens the initial impact of the rockfall energy and controls its movement down the slope. However, an attenuator allows the rock to exit the system and enter a catchment area. So hybrid barriers and attenuators combine the energy absorption capabilities of a dynamic rockfall barrier with the reduced maintenance advantages of a rockfall drapery system, one with a closed toe, as is the case for a hybrid barrier, and one with an open toe, as is the case of an attenuator. They can also withstand repeated impacts without requiring repair, which makes it more cost-effective and easier to maintain versus a high-capacity dynamic barrier installed high on the slope, which must be maintained after each impact. So they're designed to progressively slow the rocks beneath the mesh, reducing energy and bounce height, and they're particularly applicable for long slopes with available catchment space at the bottom, which can be less expensive versus draping the entire slope. Both attenuators and hybrid barriers are installed below the source zone of the rockfall and are meant to control the bounce, height, velocity, and energy of the rock. Attenuators can be installed in a series to progressively slow large rocks and guide them to a catchment ditch at the toe of the slope, or as a single structure, while hybrid barriers are designed to absorb the total energy of the rockfall. Attenuators are designed to absorb only the majority of the energy of the rocks traveling down the slope. Because of the similarities between a hybrid barrier and an attenuator, a distinction is made in relation to their application. So in a paper by Bickler in 2012, distinctions are made between drapes, attenuators, hybrid barriers, and conventional catchment barriers based on the energy absorption of the structure. Progressing left to right in the slide, drapes, shown on the far left, absorb the least amount of energy, and conventional rockfall catchment barriers, shown on the far right, absorb the most energy. Attenuators are more akin to a drape in regard to energy absorption capabilities, since it's a catch and release system, whereas a hybrid barrier has a closer relationship to a traditional rockfall barrier, since the toe of the drapery section is anchored and the rock is brought to a stop, rather than released through the toe of the slope. This slide shows the various zones of a hybrid barrier or attenuator. Zone A at the top is where the structure intercepts the rock. The barrier is designed to first intercept the falling rock, as a standard flexible rockfall barrier would. In this interception zone, the greatest dissipation of energy will occur. And then in zone B is the transition zone, where the drape section of the barrier drives rocks and debris toward the toe of the slope, slowing the speed and reducing the energy. The draped fence hangs on the upper longitudinal cable, and from a design standpoint, the heavier the main interception structure and the longer the length of the draped tail, the greater the energy dissipation in the transition zone of the system. So the energy dissipates within zone B due to the friction between the draped net and the slope surface. And then zone C is the catchment area. For an attenuator, the draped tail is open at its bottom, at its toe, to allow the rocks and debris to be free to roll out. The speed and the corresponding energy of the debris through this area will be significantly reduced due to the dissipation that has occurred through zones A and B. However, it is crucial to design a catchment ditch or a structure in this zone to collect the rocks and debris in order to avoid any rocks continuing downslope. Hybrid barriers and attenuators have grown in popularity. Although different entities have developed and carried out tests, studies, and model experiments, there are currently no design or testing guidelines or certifications for these systems. After several rockfall events and fatalities along the heavily traveled Interstate 70 near Georgetown, Colorado, and in response to a lack of success of previous rockfall mitigation efforts, the Colorado Department of Transportation recognized that the site conditions at Georgetown Pike required a new mitigation approach. So CDOT sponsored a full-scale field testing program to better understand the durability and performance of available mesh and cable net products that can be used to construct rockfall attenuators at this difficult rockfall site. The goal of the evaluation was to subject these systems and materials to realistic loading and impact conditions in order to better understand their effectiveness in dissipating rockfall energy and mitigating rockfall hazards. Some of the main objectives of this full-scale field test were to assess the performance of different types of mesh materials to rock impacts, assess the effects of rotational energies as well as the translational energies on the attenuator. One important aspect of an attenuator test is that rotational energies of the rock must be imparted onto the system. This is a big difference compared to how standard rockfall barriers are tested, with the impact only imparting translational energy. Another important objective was to assess the energy dampening effect of the attenuator tail length, which is also a critical design component of an attenuator. In order to provide controlled testing with consistent results, CDOT conducted the test using manufactured concrete blocks with a standard and consistent shape, size, and mass to reduce the inherent variability of natural rocks. A crane was then used to drop the manufactured concrete block onto a ramp, simulating energy impacts up to 500 kilojoules on a series of different mesh materials. Observations from the testing found that the combination of panel weight, tail length, and aperture size are critical elements to the function of the attenuator system. A heavier mesh in the drape section, for instance, will require a shorter tail, while a lighter mesh may be applied for lower energies and with longer tails. The added tail length, however, can result in a rigidity of the interception panel, making it vulnerable to puncture damage. Rotational kinetic energies could be as much as 30% of total kinetic energy. For reference, standard rockfall barrier testing will have zero rotational energy. It's 100% translational. It's important to note that rotational energies can impart a frictional force under the mesh that can cause tearing. The results of this full-scale field test show that Maccaferri high energy absorption HEA panels outperformed all other drapery mesh tested. The design approach for attenuator and hybrid barrier systems include evaluation of rockfall analyses to determine bounce heights and trajectories, evaluation of the dynamic impact on the barrier in order to determine required energy dissipation. This would include the expected energy level, volume, and shape of rock, evaluation of the static loading on the barrier, for example, weight of mesh, debris loading, snow loading. And from there, the important design factors include, is there a catchment area at the bottom of the slope? If not, the bottom of the drape will need to be secured in order to contain the rockfall. This will affect the amount of energy the hybrid barrier will need to absorb and the mesh weight and structural post properties. Mesh properties, of course, are important. These properties include the mesh weight, mass per unit area, mesh aperture size, and the minimum tail length of the drape section. Maccaferri solutions combine the superior quality of its tested and widely used cabled mesh, SteelGrid, RockMesh, and HEA panels, with ETA tested and certified Rockfall barrier support posts. Our reliable attenuator and hybrid systems can be fitted for a wide range of slope conditions. As you see here, given a specific energy level, the product with the greater mass per unit area will require the shortest tail length. For example, SteelGrid, with a mass per unit area of 0.5 pounds per square foot, requires a longer tail length than RockMesh, with a mass per unit area of 0.7 pounds per square foot. And the HEA panel, with a mass per unit area of 1 pound per square foot, requires the least length of tail. Finishing up with some case histories, here's a Union Pacific Railroad project where they started a modernization of track in Dunsmore, California, and had to resolve continuing safety issues caused by rockfall. So Maccaferri suggested and assisted in the design of a hybrid rockfall barrier to catch and safely control falling rock to the bottom of the slope. As you see, the upslope portion of the drapery is lifted off the slope with the post and rigging of a flexible barrier, and the drapery mesh is then laid down the slope. In this case, the high energy absorption HEA cable nets are used to add weight to the system. Rock falling from the above drapery is caught by the lifted leading edge of the barrier and guided safely to the bottom of the slope by the mesh drapery system. In response to a series of mudslides caused by fire and flood, Santa Barbara County Public Works designed a rockfall attenuator consisting of a cable net primary reinforcement with a secondary layer of double twist wire mesh meant to catch smaller debris. Both layers were polymer coated black in order to blend with the surrounding geology. At the base of the system, a rockfall barrier was installed as an additional safety measure as a debris containment structure. This is a Wyoming DOT project in the Yellowstone National Park along the Chief Joseph Highway west of Cody near the Buffalo Bill Dam. Included hanging a cable net attenuator system supplied by Maccaferri and installed by Triptech Construction. The design engineers, Ye and Associates, drew from the results of the Colorado Department of Transportation full-scale field testing of rockfall attenuator systems to specify high-strength netting of half-inch diameter cables manufactured into a cable net with 8-inch by 8-inch openings. The attenuator system extended 16 feet high and was designed with a 40-foot tail. The loss of stabilizing plants on steep grade on the eastern side of Lehigh Gap in Lehigh Township, PA, resulted in the potential for rockfalls onto Pennsylvania Route 248. The National Park Service, with funding from the FHWA, sought to stabilize the 1,000-foot high slope and protect motorists and hikers along the Appalachian Trail. This included a 2,000 and 3,000 kilojoule standard hybrid barrier with ring net panels to reduce the cost of removing the rocks after impact. And finally, this is a Washington Department of Transportation project on US 2, 5 miles west of Leavenworth. As needed, here they installed a hybrid barrier system with Maccaferri high energy absorption panels again to stabilize the rock slopes and reduce future maintenance costs due to fewer pavement repairs and less rockfall cleanup. So thank you again for attending today's webinar. I hope you gained some valuable information. Once again, I'd like to point out that there is a Maccaferri Rockfall thumb drive available with all our geohazard mitigation system, technical data sheets, product standard specifications, and typical drawings. If you would like one, please send me an email and we'll get that to you. Also, once again, we do offer a 1-hour PDH certificate for this webinar. If you'd like one, please go ahead and send me an email and I'll get that over to you. Also, the webinar today is recorded, so it will be on YouTube if you or your colleagues would like to listen again or may have missed the live stream. You may always view it later on YouTube. If there's any questions, I'm still available. If anybody is still around and you'd like have some questions, I'd be perfectly fine to stick around and answer them for you. Thank you again.
Thank you so much for that, Mike. That was a really great presentation on rockfall barriers and hybrid barriers and attenuators. We have a couple of questions in the chat so far. First up was from Francisco Silva. What has been the measured performance of rock barriers against debris flows? Can you refer to examples that successfully contained a moderate size debris flow?
We do design debris flow barriers differently than rockfall barriers. They are custom designed, and we have performed, testing also on debris flow barriers. Occasionally, like you said, there's rockfall barriers that are then subjected to debris flow-like conditions, and they do generally perform well. But for the most part, they do, and that has occurred. I think I showed a case history early on of a rockfall barrier, a 3,000 kilojoule rockfall barrier that was basically overwhelmed by a debris flow and energy impacts on the order of 4,000 kilojoules. Obviously, there was a lot of damage involved, but it still performed in terms of prevented the hazard from moving down slope. So you would expect some damage to occur with a conventional rockfall barrier being subjected to a debris flow.
That's great. I bet in a situation like that, the Hellomac system would come in handy, especially in a remote setting. We received another question in the chat from David Field. Where are products manufactured and availability timelines for delivery once designed? So kind of a production and
Good question.
Yeah.
So Maccaferri manufactures everything. Well, yeah, we generally supply a standard product, everything but the posts. The posts, we use steel fabricators in different parts of the country. The post is the longest lead time item. We generally tell our clients 4 to 6 weeks for post fabrication and then galvanization. Generally, we come in less than that, but our standard claim is 4 to 6 weeks, and once again, usually it's sooner than that. So that's for the post. Everything else is within it's either standard product or it's product we generally have in inventory. That's not a problem. Lead time is not a problem with any of those items unless something needs to be sent out for powder coating. But usually it's the post that is going to be the longest lead time item. So 4 to 6 weeks is a typical range.
Makes sense. Gives the contractor time to mow up to site and start drilling anchors and set up their alignment.
Yeah.
And speaking in alignments, do you have any rules of thumb for alignment of barriers, like the difference between a concave, convex, or straight alignment? Would you prefer any of those to another?
We would generally prefer straight alignments. So we'll break up the segments into straight barriers and then set the alignment based on straight barriers. Yeah.
Gotcha. We received another question in the chat from Ingrid Eckersberg. Are there any considerations for wildlife movements, especially with Jersey barrier installations?
Occasionally that comes up, and I don't really have a good response to it. So I guess DOTs don't seem to be all that concerned with it, or they've figured out that it's not a problem. So I'm sorry, I can't really answer that in much detail.
That's okay.
Probably might be a better discussion with a local DOT representative that might have a better understanding as to what they have seen.
That makes sense. One other question that I had was, after a barrier does experience impact, how would you evaluate the anchor integrity?
Well, I mean, they could perform, you know, a pull test would be the, you know, the most direct way. Yeah, so.
So aside from checking for making a visual observation, if there's any visual or surface defects, kind of the next step before drilling a new anchor would be doing a pull test, making sure its structural integrity and capacity is still available prior to getting out the machinery to re-drill a hole. Makes sense.
Sure, that would be last resort.
Great. Well, I think that's all. Well, we don't have any more questions in the chat. With that, I think Brad might like to close this up.
I will, absolutely. Thanks, Sebastian, for moderating today, and thanks, Mike, for another good presentation. And for all of our viewers, we appreciate you sticking with us, and especially those who answered questions and or asked questions and responded to my poll questions and everything. We really appreciate that. Thanks for the interactivity. As we mentioned at the beginning, this was the third and final part of the Maccaferri Live series. We've put the presentations in a playlist for you on the YouTube channel. So if you'd like to go back and watch the other ones, just look at the playlists on the GI YouTube channel. The Maccaferri series will be right there, and you can watch all three in order. You could watch them out of order. You could be crazy, do anything you want. Just watch them. That's all we ask. So we really appreciate this, Mike. It's been a good spring with you guys and getting to know your products and hearing about them. And hopefully you get some good questions from the crowd about it. And we really appreciated having you. So thank you for doing this.
Yeah, well, thanks for having us, Brad. I really enjoyed it. Look forward to lining something up for the future. I appreciate the audience for sticking around. I know it was a little long today. And thanks to those of you that managed to stick with us. So appreciate it, and feel free to reach out to us if we can be of any support to you in the future.
And again, for our viewers, you know, we've got so much more great content up on the YouTube channel. Feel free to click around and browse, like, subscribe, and do all that stuff so that you know every time we post something. It's going to be a while before our next live stream. The next YouTube event is May 14th, and that is the premiere of the next Geo Legends episode. This is one we filmed live at Geo-Congress in Vancouver this year, with Matt Evans interviewing Ed Kavazanjian from Arizona State University. So you'll want to be around for that. You can sign up at our Eventbrite page, as you can for all of our future live streams. So for all of our viewers, again, thanks for sticking with us today. Our producer today was Amber Davis, and we will see all of you next time. Have a great spring.